solution that contains a weak acid and its conjugate weak base. Remember, a conjugate means it differs by an H+. What's special about buffers is that you can add small amounts of strong acid or strong base to the buffer, and the pH barely changes. So meanwhile, if you added a tenth of a mole to a tenth of a mole of a strong acid to a liter of water, you're going to take the pH from, let's just see that, 1 liter of H2O. It's got a pH equals 7. If I add a tenth of a mole of hydrochloric acid to this water, the pH is going to go from 7 down to 1. So it changed by a factor of 1 times 10 to the 6th, a millionth. That's changing by a factor of a million. That's a huge change. So if you add strong acid or strong base to water, the pH changes significantly. But if you add small amounts of strong acid or strong base to a buffer, what happens is, well, we said both the weak acid and the weak base are present. So let's say I've got, this is my generic weak acid, by the way. Whenever I get some name and I'm like, I don't know what methanoic acid is, but I do, I'll put something like that. Like, oh, acids have an H. This would be the conjugate base. So if I've got this buffer, I have both of these things present. If I happen to add some strong acid, and by the way, like, hydrochloric acid, it's bad. You stick your finger in it, you lose some skin. It's bad. Weak acids, like vinegar, they're tasty. Put it on your salad. So while we are afraid of the strong acids because they dissociate 100%, weak acids, they're not so bad. Well, what happens if you've got this buffer, and if you added some strong acid, like hydrochloric, it's just the H+ that we care about. If I added hydrochloric to this, the hydrochloric is attracted to the conjugate weak base, so I'd be adding H+ right here. We know that they react 100%. Let's say this buffer has a mole of weak acid and 1 mole of the conjugate weak base. If I added that tenth of a mole, so 0.1 moles, well, it's going to react with this guy. So now they're going to react 100%, and I'm going to lose this tenth of a mole. I'm going to lose a tenth of a mole here, so it becomes 0.9, and I'm going to gain a tenth of a mole here. Okay, well now I'm back to having this weak acid and the conjugate weak base. And I'm again back to not really being afraid of this thing. So it still ends up being a solution that contains weak acid and conjugate weak base, and the pH will barely change. So buffers are special and important because they avoid changing pH. We care about that because like your body is, contains tons of solutions, and if you change the pH drastically, the cells in your body are going to fall apart. Enzymes aren't going to carry out what they're supposed to do. So you don't want pH to change, so buffers in your blood are the reason you are alive. Let's look at a buffer. So we've gotten pretty good. We've been practicing, and it takes more practice. We've gotten pretty good at finding out if I have a buffer. So when you have a strong thing, figure out what the strong thing reacts with, and find out, do I have moles of weak acid and conjugate weak base, or moles of weak base and conjugate weak acid left? If you do, you have a buffer. And to solve for the pH of a buffer, we haven't done that, you're going to use the Henderson-Hasselbalch equation. Only use it with buffers, so weak acid and conjugate weak base. This is the equation you're going to find on your Greg sheet. It's pH equals pKa plus log of your base over your acid, your weak base over your weak acid. POH is the same thing, but opposite. So instead of pKa, pKb, instead of log of base over acid, it's acid over base. And the things that you're going to use, pH is the negative log of H, so pKa is the negative log of the Ka. Ka being the equilibrium expression for acids, Kb being the equilibrium expression for bases. So your pH will be always really similar to the negative log of the equilibrium expression, and then adjusted based on how much base and how much acid you have. You can use moles or molarity for that weak base over weak conjugate acid. And the reason is, if you figure you have, let's say we had 3 moles of our weak base divided by, let's say, 2 liters, all over, I'll say, 1.5 moles of the conjugate weak 2. And the 2 liters cancels out. You know, 1 over 2 liters divided by 1 over 2 liters, it's just 1. So that's the reason I could have said 3 moles divided by 1.5 moles. Well, that's just going to give me 2. Or I could have said 3 over 2 is 1.5 divided by 1.5 over 2.75. Also gives me 2. So, okay, so this is our equation. When you forget it, negative log the Ka. P is also explained on your Greg sheet. And then log of either moles or molarity, just be consistent, of the weak base over the conjugate weak acid. Let's do one. What is the pH of a 1 liter of 1.5 molar acetic acid, that's vinegar, it's tasty, that has 2 moles of solid sodium acetate added to it? So, and we're going to assume there's no change in volume. So I had 1 mole. When I add the solid sodium acetate, it's still going to be, I think I said 1 mole. I have 1 liter. When I add the solid, it's still going to be pretty much 1 liter. So let's write out the equation that I have. I have sodium acetate and acetic acid. Since they're conjugates, I'm going to put them on opposite sides of the arrow. They're not going to react with each other. Conjugates go on opposite sides. So acetic acid, that's the one acid that doesn't just jump out at you and look like an acid. So acetic acid, and I like to put my weak acids in water. And then acids lose an H, so acetate, CH3COO is a 1 minus. I'm going to leave the sodium off because it is an alkali metal, and we know alkalis don't do anything. So when that H is given up to water, I've got this guy. So this is the equilibrium that I've got going on. And this problem is really nice because it's telling me this is the molarity of the acetic acid that's present. And if this is 2 moles over 1 liter, this will also give me the molarity of the acetate present. So this is 1.5 molar. This is 2.0 molar. And you know how usually we start with some kind of ICF table because we've got a weak thing reacting with the strong thing? This is actually telling you what you would have had in your final step. You know, it's taking that whole ICF and making it unnecessary. So I can say, well, I've got this weak acid and its conjugate weak base are present. Since they're weak, if you'd like, you can solve this as an equilibrium problem into your minus x plus x, use the Ka expression for this, and you'll get the right answer. That'll work. Or you can say pH equals pKa plus log of the base over the acid, because it's a buffer. So I'm going to negative log this, and when you negative log that, you get 4.7447, okay, plus log of base over acid. So that's going to be 2 over 1.5. I could use moles or molarity either way, and I'll get the same answer. Okay, so log of 2 over 1.5. When I log that, make sure you try that at home and can do that because, well, you know, I'm going to write down an answer eventually. So, okay, so the pH is really similar to the pKa, and it's slightly adjusted by the amount of base and acid. In this one, I can see I've got more base than acid. Basic things raise the pH, so it's going to be the pH is really close to the pKa, but slightly higher. And it is. So I ended up with 4.87. Do I have 2 sig figs everywhere? I do, so I put 2 sig figs. So that's the answer. Yay. Here's another buffer problem that has the ICF table in it, I'm pretty sure. Yep, it does. So I have hydrochloric acid and ammonia, this weak base. I know they're not conjugates. I'm going to put them on the same side of the arrow. And since it's a strong thing, it's going to react 100%. The H is going to go to that. So NH4, the plus, and I'm left with this chloride behind, which I really don't care about because it's a spectator ion. Won't do anything. So I'm going to do my initial change final. And for this kind of table, I have to use moles. So my students remind me when I forget, which is awesome. So this is 1 molar, and there's 50 milliliters, so that is 0.8 there's 0.05 liters, 1 molar, there's 0.05 moles of the hydrochloric acid. The ammonia, we have 0.15 liters, and it's 1 molar. So 0.150. And so then I know that I have less hydrochloric acid. There's this 1-to-1 ratio, so I'm going to use up all the hydrochloric acid. 0 minus 0.05 gives me 0.1 plus 0.05 on this side, 0.05. Okay, so in the final, which is where I started in that last problem, this problem actually made me do that work. Here I see I've got this weak base and its conjugate weak acid are both present. This is a buffer, so its pH is going to be really close to the pKa of the acid. This is the acid because it gives up the H, that's the base. I could also go POH equals pKb plus log of base over the acid. Either way is totally fine. I either have to solve for Ka or I have to solve for pH once I get the POH. I think I'm going to go and solve for the Ka. So also on your aggregate sheet, you see that Ka times Kb equals Kw. Kw is that constant. It's 1 to the negative 14th. So I've got the Kb. So Ka, divide both sides by Kb. Ka is equal to this Kw, 1 times 10 to the negative 14th, constant, divided by Kb, 1.8 times 10 to the negative 5th, and that ends up being 5.5, on and on and on, times 10 to the negative 10th. Okay, that's the Ka of ammonium ion. So then I can say pH is equal to pKa of the ammonium ion, because that's the acid, plus log of the base over the acid. The base is this guy, 0.1 over 0.05, so really log 2. I know, so 0.1, 0.05. Good. So pH, let's see. When I negative log that, I get 9.255 plus 0.301 for this, so you can see if you did both parts right, and then addition. 9.56 is the pH I get. And I've got 2 sig figs everywhere, or 3, so that is your answer.